Good evening, everyone. Myself, Sana Sheikh, a first year PhD student from IIT Bombay. Today, I am going to take your live session of NPTEL course, that is Symmetry, Stereochemistry and its application. The course instructor is Professor Anshuman Roy Chaudhary from ISR Mohali. In this live session, we are going to discuss the previous year assignment question based on our topic. I hope all of you have done the week 1 assignment questions. Now today we are going to discuss the week 2 assignment questions. In previous lecture, we have discussed IUPAC nomenclature and question based on that topic. So before moving further, I would like to tell about today's lecture. So today we are going to discuss the group theory, that is point group of the molecules. So please pay attention, and if you have any question, any doubt regarding these questions, you can ask me now. I would love to help you for solving these questions. So this is the question number 1. So determine the point group of the following molecules. So before solving the question, you should know what is point group. The point group is nothing but it is a set of all the symmetry operations that can be performed on the molecule, and it results in a conformation indistinguishable from the original one. That means we have that symmetry operations. Suppose like C2 axis or C3 axis, like uh, center of inversion, or we can say plane. So these are the symmetries which include in point group. So in point group, basically we have all the symmetry operations. So I hope all of you have seen the lecture, and it will help to solve this problem. So this is nothing but the 1, 2. I will write here. This is nothing but 1, 2, 4, 5 tetrabromobenzene. In IUPAC, we have covered this portion. So this is the 1, 2, 4, 5 tetrabromobenzene. So how many symmetry elements are present in this molecule? Anyone can tell me? If you will see here, in symmetry, you can if you will pass the plane over here, you will see that both the portion from from right hand side and left hand side are identical. We can say indistinguishable. Yes. Sorry, I didn't get what. Anyone have question? If you have doubt, you can ask me during the class also. So we have here symmetry plane. So if we will pass the plane over here, we will see that we have two indistinguishable images of each other. So and if we will pass plane from here, we will see again these two parts are indistinguishable. This one and this one. So that's why we can say here we have two planes here, but which axis we will take here, we have to find out the rotation axis also. So which axis is present here? If you will consider this as a center, and we will pass the, see, this is the 3D image of this tetrabromobenzene. So if we will pass here axis, pass the axis from here, and we will rotate this molecule by 180 in any direction. We will, what we will get, suppose if we are rotating molecule in right hand side direction, then what will happen? This molecule, this atom will come upside and this one will goes down, this second one. So that means it will become an indistinguishable image and this one will be replaced by this one. So but both all four atoms are bromine atom, that means it will become indistinguishable image. That means here C2 axis is present. C2 axis. How many other C2 axis are present here? Anyone? One C2 axis is from this center. Now the other C2 axis is also present. We have to find out here. The other C2 axis is perpendicular to this axis. Perpendicular, that means from here. Sorry. If we will see, if we here we have another C2 axis perpendicular to the first one. That means if you will rotate on this axis, you will get the indistinguishable images because these two atoms will interchange each other, and here these two will interchange each other. So we will get in distinguish indistinguishable images of each other, which is looking like identical. So that's why, that means here we have two C2 axis, one perpendicular to each other. That means we have principal axis C2. Whenever we are having both the axis, principal axis and subsidiary axis, we are writing D for point group. Now principal axis is also C2, that's why we have to write here 2, D2. Now we have to find out the plane present in this molecule. Which plane is present? As we have discussed before also, here as I told you, we can pass plane over here. Not exactly. When we will pass plane from here, we will get mirror image of each other, both the side. When we pass sigma plane, that means we have here C2x, sorry, not C2x, sigma h plane, because this we have considered this axis as a C2 axis, principal axis. That means this plane is uh, parallel to this C2 axis. We are doing passing this plane parallel to this axis. That means this is a sigma v plane. Sigma v plane. Now you can see here we have here horizontal plane also. If we will pass plane between these atoms in horizontal way, like this way, if we will pass in this way, then all the atoms will cut into two parts and it will become same as it is. Molecule is looking like here. That means it will become indistinguishable image. That plane is perpendicular to principal axis. That's mean it is a sigma h plane. So as from the point group rule, we are writing the plane perpendicular to the if plane is present perpendicular to the principal axis, that's then in that case we are writing h over here. That means the point group of the following molecule will become D2H. D2H. I hope all of you clear in this question. So now we will move to the next question. Yeah. Here we have to find out the point group of this complex molecule. So what is this actually? This is nothing but M is a metal here. Metal. Any metal. And this is a ligand attached to the metal. So this is a bidentate ligand here. Ethylene diamine is bidentate ligand. It can bind from this side also and this side also. So this bidentate ligand is 3. That means it is a hexa coordinated metal complex. Hexa coordinated means each ethylene diamine is binding by two sides, and we have 3 ethylene diamine. That means we have hexa coordinated metal complex in this way. You can see here. So if this is the complex is for which we have to find out the point group. So you can see here, this dash bond is back side, and this wedge bond is from for front side, representing the front side. So we can pass C3 axis over here. If we will pass C3 axis, it will rotate in this way, and we will get indistinguishable image from the original one. Now here one C3 is present, that is a principal axis. This is principal axis. Now we have 3 subsidiary axis here. 3 subsidiary axes are passing through this way. Like if you will consider this way, this plane is if you will rotate by 180, you will get again an indistinguishable mirror image from of this compound, which is also shows the uh, shows the same symmetry. Then we are passing the through this axis, and again you will get the C2 axis here, and this one is also the same one. So here we have 3 C2 axis, 3 C2 axis, and one C3 axis, one C3 axis. That means now we can write here, because on the basis of principal axis we are writing here 3, and both subsidiary and principal axis are present. That's why we are writing D3. Okay, D3. Here you can see in 3D image. See, this is see here. This is one ethylene diamine molecule. This one is the second one, and this one is the third one. Here also, this one is one ligand. This is the second one, and this is the third one. One atom is hidden behind this atom. So don't think this is the one atom. Here, one more atom is here, which is hidden behind this one. Now you can see in this 3D model easily that here you can see the axis passing through the center atom, and between these two bonds is C2 axis. Is C2 axis. If you rotate on this axis by 180, you will get the indistinguishable mirror image of the original molecule. Original molecule. Here again, if you will pass the C2 axis through the center atom and the another ethylene diamine molecule ligand, then again you will get the same indistinguishable image of original one. And again here this is the third C2 axis, as I have discussed earlier. Third C2 axis. There are 3 C2 axes. Now in the second image you can see here, this is the principal axis, which is perpendicular to all these three C2 axes. You can see clearly in the image, it is perpendicular to all 3 axes, and it's passing through only the center atom, not through the ligand atom. Only through the center atom C3 axis is passing. That's why we are writing here D3, because it's a principal axis. D3. Now any other point group is present here, or any plane, or any inversion center, or any else symmetry element? No. If you will pass plane over here, you can see, if you will pass plane through this one, it will become non indistinguishable image, means this atom will uh, come here or next to back side of this atom, and this one will go this way. So it will not become the same one, because here we can see here this atom is upside. If it will go downside, it will not become the same as the original one, so it will change. That's why there is no horizontal plane. Now let's talk about the vertical plane. If we will pass the vertical plane through here, then we can see this atom is here and it will go to this side. So this one is downside, this one is upside. If we will pass the plane, it will go upside. That means it is not the same as original one, because in original one here downside atom is there, but it will become upside. That means there is no vertical plane, there is no horizontal, no vertical, no dihedral plane. That means this molecule have only D3 point group, D3 point group. So the point group of for this molecule, this complex will become D3. I hope all of you are clear here. Let's move to the next question. This is the which molecule is this? Anyone can tell me? This is a dichloroethylene. So here in dichloroethylene, this is a trans one. Both cis and trans conformations are possible. Configurations are possible. So here we have trans ethylene dichloride. So dichloroethylene we have here. You can see this is the plane. This is the plane. As I shown here, this is the plane. If we will pass the axis here, C2 axis, this one, C2 axis, this chlorine one will come on this side, and this chlorine will come to this side. That means it will become again the indistinguishable image of the original one. Not the identical, but indistinguishable, because it is not identical because the atom number is not the same atom is not here, atom is moving, but because the atoms are same, and it will look like indistinguishable image. That's why we are calling indistinguishable. And here C2 axis is present. This is a C2 axis present here. Now any other axis is present here apart from C2? Anyone? Here one C2 is there, right? Any other C2 or C3, any other axis is present here? No. If we'll pass here axis from here, what will happen? This chlorine comes to this side, and this proton will go to that side. So in original one we have here here chlorine, but if we will rotate by C2 axis or any other axis, we will get H here. That is not indistinguishable image of the original one. That's why this C2 axis is not valid. It's not valid. Now if you will see here, you will see here, if I will pass plane over here, plane, if on this plane will cut this molecule into two halves, all the atom will cut into two halves. That means it will become indistinguishable image from the original one, because all the atoms are cutting same way, and the image downside of this plane will look like same as the original one, as an original one. So that's why here sigma H plane is present, and here C2 axis is present this way. Okay, that means we have C2 C2 axis is that, that's why, and horizontal plane, that means C2H. Point group for this molecule will become C2H. All of you got it? Okay. The next one is allene. This is 1,3-dimethylalene. If we will talk about simple allene, then we will get the different result. But here we have 1,3-diallene, dimethylalene. That means it will not give the point group say as allene is giving. So here we will see that this is our molecule. Here you can see the rotation here. So here one C2 can pass over here, as you can all of you can see here. C2 is passing through this angle, and you are getting indistinguishable image of original one. I'll show here. See here. If uh, suppose this is on plane, this is back side. If you will pass axis from here, consider this way, tilted way. You can see this in this image. This is a tilted way. If you are passing axis through here, it will give you indistinguishable image of the original one. That means here C2 axis is present. Now you can check here any other plane or axis is present or not. Any other plane or axis is present or not here. If see here, if we will check plane first. So if we will pass plane through here, this way what will happen? This will come to here and this will come to that side. Now in original one we have CH3 over here, but if you will pass the plane we will get H here. That means it is not the axis present in this molecule to get the indistinguishable image of the original one. That means there is no horizontal plane. Why I am talking about horizontal plane? Because this plane is perpendicular to the principal axis. Here principal axis is C2. We don't have here any subsidiary axis. If you can check here, if you will pass the axis over here, you will rotate by 180. You will not get the same compound as we have uh, as we have original one. So there is no subsidiary axis, no plane. Now we will check vertical plane also. If we will pass the plane like this one, what will happen? All the molecule will reflect behind the plane. Reflect behind the plane. So this is the back side of the plane. This one. So this atoms are on plane, but this is the back side of the plane. Back side of the plane will come upside, and upside one will go down if you will pass the plane. That means it will not remain identical from the original one, because CH3 will come on wedge and H will goes to dash side. That means it is not the plane we can consider here. This plane is also not there. That means only C2 axis is present in this molecule. So the point group for this molecule will become C2. C2. This comes under CN point group. CN. Like we got D3 plane. Same D3 group point group. Same here we are getting CN. C2 point group. You can see here C2 axis is present if we are passing through here, but this C2 is not present. You can cross check this one. Okay. Now next question. What is the name of this molecule? We have discussed IUPAC nomenclature. I hope all of you are able to find out the name of the molecule. Here all the four carbons have bromine substitution. That means we can consider any of the carbon as 1. So we don't have to give number here also because all the atoms are same. So this is the tetrabromocyclobutane because 4 carbons are there. Tetrabromocyclobutane. Now which symmetry elements are present in this one? You can see here. This is a 3D image of the molecule. This red atom is nothing but the bromine, uh, which is downside. Now this small atom is hydrogen. This is hydrogen. Now you can see here on one carbon, one bromine, one hydrogen is present. Then another one is also containing the one bromine, one hydrogen. Same for this one and this one also. One carbon is hide behind this atom. So don't think here 3 carbons are there, 4 are there. You can see in this image 1, 2, 3, 4 carbons are there, and all have one bromine and one hydrogen, and these bromine and hydrogens bromines are trans to each other. You can see here this is downside and this bromine is upside. This one is downside. Same here also, this one is upside, this one is downside. If you will compare between these two, and in these two also, this is upside, this is downside. This is nothing but the 3D image of this same molecule, the same molecule. Now we will discuss the plane and symmetry element present here. If you will pass the axis through here, I am taking the center of this molecule here. Yeah, suppose. Here we have axis. This is below the plane. I am considering cyclobutane as a plane, and this is below the plane, this is above the plane, this side. Now we are passing axis. Which axis is possible? See, if I will pass like it has 4 carbons, so if I will pass C4 axis, suppose I'm just checking here, telling explaining you to how to decide which axis is present. Now if I will pass C4 axis, that means it will rotate by 360 divided by 4. How much? 90. Right? That means I have to rotate it by 90. Okay. If I will rotate it by 90, that time that means what will happen? This upside bromine will come to on this side upside, and this downside bromine will come here downside. If you will see compare with the original one, you will see here in the original one we have here bromine downside, back side of the plane, below the plane. But when we will rotate by 90, it will come upside. That means there is no C4 axis is present because it is not giving the indistinguishable image compared to the original one. That means C4 is not present. Now we will check other axis also. C3 is not possible. You can check cross check by yourself. Now we will pass the C2 axis. C2 axis. C2. If we will pass C2 axis, this molecule will rotate by 180. 180. That means this bromine will come this side. This is upside, that means it will come upside, and this will go this side. Same with this one, this will go this side, and this bromine will go this side. So you can see here upper one will remain up one only when it will be rotated by 180, and below one will become below one if rotated by 180. That means there is no change in the stereochemistry or the molecule in from the original one. That means it is an indistinguishable image of the original one. That means C2 is allowed here. C2 axis is present. We have C2 axis here. One C2 axis. Now we have to find out other C2 axis present here. Which other C2 axis are present here? Anyone? Okay. The other C2 axis present here is, you can see from here, this one, C2. If you will pass the axis through here, you will see it will be rotated by 180, right? After 180 rotation, it will this bromine, this one, this bromine will come upside and this bromine will go downside. You can rotate in imaginary way. You can see in 3D plane also. If I will pass C2 axis here, it will, this bromine will go down and this one will take this will come upside. Same here also. So it will give a indistinguishable image from the original one. And because the position of the bromine will remain same, like up here we will get upside bromine and here we will get downside bromine. The atom is changing, but we are getting the same image as the original one. That's why we will consider this C2 axis also, and that means we have C2 the second C2 axis perpendicular to the first one, perpendicular to the first one. How many C2 axis? This one from here, the other one was from here. Any other C2 axis? Yeah, you can see from this side. Here also we have C2 axis. So we have two subsidiary axis and one principal axis. When we have subsidiary and principal both the axis symmetry axis in the molecule, that time we are writing D. And here we have C2 as a principal axis. That means we have to write here D2. D2. Now any other plane is present here? Any plane of symmetry? Can you pass the plane through these two C2 axis? If we will pass plane through here, what will happen? You will see this downside bromine will come this side, this bromine will go to that side. But if you will check here, this will not look like the original one. This is not the indistinguishable image of the original one, because here we have upside bromine. But if you will pass the plane, it will come here downside. That means this plane is not present here. This sigma H plane is not present here. Sigma V, sorry, this is the parallel to the principal axis. That's why sigma V plane is not here. Now we will check the horizontal plane also. Any horizontal plane is present here? Horizontal means perpendicular to the principal axis. This one is our principal axis. If we will pass plane here through here, we will get the inversion of all the bromine atoms. That means we will not get the image or molecule uh, which will resemble the original one. We will get the different one, that is not the indistinguishable. That means sigma H is also not present here. Now check we will check for the dihedral plane. and dihedral plane is present here. What is a dihedral plane? Dihedral plane is a plane passing between the two subsidiary axes. Here we have two subsidiary axes. One is this one, the other one is this one. Two subsidiary axes, and this one was our principal axis. Okay. So the plane passing between these two planes, like if we will pass plane this way, wait. If we will pass plane this way, considering these two atoms and these two atoms passing through these four atoms, then if we will see this side of the plane, this side of the plane and this side is identical. These are indistinguishable because here bromine is upside, here also bromine is upside. That means we have here plane of symmetry. Here, after passing the plane, we are getting a symmetrical half. Symmetrical half. That's why it's the plane of symmetry. So here we have sigma d. Sigma d means dihedral plane is present. The plane is passing between the two C2 axes. That's why we are calling it dihedral plane. So here dihedral plane is there. The another dihedral plane is passing through other two bromine. I will show here. Here you can see the another dihedral plane. From these atoms. This is the another dihedral plane. Because this half and this half are identical or indistinguishable. That's why we will consider this as a another half and symmetrical. That's why two dihedral planes are present. So because we have here principal axis, subsidiary axis and dihedral plane. So for principal axis and subsidiary axis we are writing D. I will write here D, because the principal axis is two-fold axis, that means D2, and uh, here we have sigma D present, that means we are writing here D, D2D. The point group of this molecule is D2D, D2D. Clear? Let's move to the next question. I have missed one question here. I will write here. The next question is metal diethylenamine trans complex. I will write in that form: metal bracket NH here again NH2 twice NCl Cl2. This is the trans one. So we have to find out the point group of this molecule, trans. So in center we will have metal, then ethylene diamine, because we have two ethylene diamine. I am drawing like this way. This is a trans complex, means both the chlorine will be trans to each other. Will be trans to each other this way. Now you can see here, this is a octahedral complex, and we have to find out the point group of this molecule. So can we pass the plane through perpendicular to these two chlorine atoms? That means this way. This way. Can we pass the axis? First we will check symmetry axis. Rotation axis here. If we will rotate it by 180, we will see here by 180, you will get the indistinguishable image by C2. Indistinguishable image from the original one, right? You cannot pass C4 axis because you will not get the identical image as this one has. So we have here C2 axis. Now any subsidiary axis is present? Yes. From here, if you will pass C2 axis from here, you will get the again the identical one, indistinguishable one. And one more C2 axis is possible through this side, right? So here, how many C2 axis are subsidiary axis are present? 2, and one is a principal axis because it's passing through the molecule, through center metal, central metal. So here we have 2 C2 axis and one is principal axis. Now we will check other planes present here. Any plane of symmetry is present here? Yeah. If we will pass plane perpendicular to the principal axis, we are considering this axis as a principal one, passing through the metal. Okay, this way. So this one is perpendicular to the principal axis. That means this is the sigma h horizontal plane, and you will get the indistinguishable image from the original one. But here other symmetry plane are present or not, we have to check. If I will pass plane vertically, that means parallel to the principal axis, then what will happen? You will get the indistinguishable image. Again the indistinguishable image from the original one. So here you can pass plane parallel to the principal axis, you will get sigma b. Here sigma h. Here both the planes are present. That means we will write here D for both the axis, subsidiary and principal axis. Because the highest rotation axis is C2, principal axis is C2, we will write here D2. 2 here. Now here we have sigma b as well as sigma h also, but the sigma h is perpendicular to the principal axis. That's why we will write here h. H means horizontal plane, because this is perpendicular to the principal axis. We are considering the plane perpendicular to the principal axis here. The point group for this molecule will become D2H. D2H. I hope all of you are clear. Now, this is the second part of the question assignment. Here we have to draw a Newman projection of the molecule. So you can see we have to draw the Newman projection for this one, this molecule. You can see here, this is the, what the molecule name is? What is the molecule name? N-butane, because 4 carbons are present here and this is a linear chain. That's why it is N means normal butane, N-butane. The name of this molecule is N-butane. Now you can see here we have to consider these two atoms for Newman projection, which is marked by star here. Which is marked by star. But when we will consider these two atoms as a Newman projection, you can see here, this is the carbon 1. I am giving here number 1, not 1, I will write this way, 1, 2, 3, 4. So I am giving here 2 and 3 carbon to the star carbons. So this carbon is, the front carbon is 2 and the back carbon, this is showing the atom of carbon. So this is 3. Now you can see here, these are trans to each other, but we have to draw here eclipse conformation. Eclipse means what? The atom will come with the same angle difference to the behind carbon atom. That means the angle between these two will be 0. These two atoms will be 0. This is a eclipse, means it will overlap one atom to the another one, overlapping of the atom. This one is the anti-conformation, staggered conformation, and this one is the eclipse one. So in eclipse one there are two possibilities. One is this one, that means consider this methyl group here and the other hydrogen are from these two are the other hydrogens, and from front side this methyl group is this one. If you will draw the Shoher model, you will understand this way. I will draw this way. Suppose this is your C2. I will not write 2. If you will draw Shoher's model, see this way. So here this is our first carbon, this one, and this one is our this carbon. And here we have methyl upside. I will write here CH3. This is CH3. Here we have here downside. I will write this side CH3. Now in Newman projection we are looking from this side. That means this carbon is coming first, and the behind this carbon C3 is just behind the this carbon atom, as we are writing here. This is the eclipse one. Why eclipse one? Because you can see this upside atom is parallel to this upside atom, and this downside atom is parallel to this one, and this one will overlap by this one. All the three atoms are overlapping on each other. That means the angle between the inclination angle is 0. And if you will draw the staggered one, what will happen? It will look like this way. The angle between the two atoms will be 60. You can see here this way 60. So here, because we have to draw the eclipse conformation, that's why I'm considering this one. Now you can see here we have one CH3 here. Draw from this side. One CH3 we have here. Now this CH3 is on this side, that means here, right side, left side, and others are hydrogen atom. This eclipse conformation have low energy compared to this D eclipse conformation. These two are and staggered and anti staggered conformation, anti and Gaussian. So ignore these two one. But these are the most stable. Anti is more stable compared to the eclipse and Gauss interaction, Gauss conformation. So anti one is more stable, but here we are talking about only eclipse one. That's why we are not ignoring staggered one. So in this B and D, B1 is more stable and D is also the eclipse one, but have high energy, because here CH3 interaction will be higher. Energy between of this interaction will be higher compared to the hydrogen and CH3 energy. That's why it is less stable. High energy means less stability. High stability means less energy. So here, because CH3 interaction will give higher energy, it is least stable compared to this one. So these two are the eclipse conformation of the uh, N-butane molecule. I hope all of you are getting these questions. Now let's move to the next one. This is again the same molecule as N-butane, but here this time we are considering the different atom. In previous slide we are considering C2 and C3. Here we are considering C1 and C2. If we will take C1 and C2 and draw the Newman projection eclipse, we will get this one conformation. There is no possibility of any other conformation. In previous one we were getting the two eclipse conformation, because we were considering the direct CH3 interaction and CH3H interaction, but here there is no possibility, because this carbon have all the atoms are H only, hydrogen only, all are same CH only, CH3. That's why it will give only one conformation. Here you can see CH2 CH3 will uh, taken backside, because C2 is considered the backside atom and this one is a C1 as I have drawn here, and C1 has all three hydrogen, and the angle between hydrogen and ethyl is 0. Here 0, that's why it's eclipse. This is the eclipse one. How to draw, I will discuss here. First, now you have to draw Schauer's. It will become easy to understand. In Schauer's projection, you have to take two atoms which you have to consider for Newman projection, right? Now take two atoms this way, because we are drawing eclipse, so we will write this way only. This should this atom should in same plane with this one. You have to imagine in 3D. Now these all atoms are overlapping. Now consider this one as a front side carbon. I will draw this in different way, then it will become easy to understand. Okay, this way. Okay, So I'm considering this one as a C1, this atom, and this is C2, 2, 1. So C1 has all hydrogens here. First you have to draw in this way, then it will become easy to understand. See, you have to draw hydrogen on all their carbons. Now in on second carbon you can see this upside bond has ethyl group, and this is a plain side, and that means on back side we have hydrogens, and upside also we have hydrogen on wedge also. That means you have to take on plane C2H5, C2H5 group, ethyl group on plane, and this is the below the plane H, this is above the plane H. Now look from this side and draw. This is the back side carbon, this is the front side carbon. Front side carbon is looking this way, front carbon, and the back side carbon is also in same way. See here, right? Front carbon has all the atom H. I'm writing H, and backside carbon have two hydrogens here. Just look this way. It will right hand side we have hydrogen. Here right hand side we have hydrogen. Here left hand side we have hydrogen. I will write here hydrogen. Now below side we have C2H5. I will write C2H5 here below side. Right? Now you will see here, this is the eclipse conformation for this molecule, and this one is correct. These both the eclipse conformations are same. Just if you will rotate it by 180, you will get the same as drawn here. These are two identical one. So these are the same. So this one is the correct eclipse conformation for this and butane with carbon C1 and C2. I hope you got it. How to draw Newman projection. Now the next one is an pentane. This is a pentane. 5 carbons atoms are there, but we have to draw the eclipse conformation with respect to C2 and C3. Why I am telling C2 and C3? If I will count from this side, it will become C3 and C4. As I have discussed in previous lecture, we have to always take the lowest numbering. We have to consider the lowest numbering. From this side, we will get the lowest numbering. That's why I am considering this 2. You can here you can take any side, because it is a identical sorry, all the carbons are same, but in case of functional group we are following that rule. So I'm calling this one as 2 and 3 because it, we are considering these two carbon atom. Now here if you will see, there are many possibility for eclipse conformation. This A is eclipse, this one is staggered, so we will ignore this one because we want only eclipse one. This is eclipse, this is again staggered, this one is eclipse, this is staggered, and this one is eclipse. How many eclipse conformations are there? 4. Among these 4 conformations, we have to find out the stable one conformation, and we have to draw that conformation. So again we will approach the same way. This question also we will approach in the same way we have done for previous one. You have to draw first This way it will become easy to understand. This way. Now this is a 2 carbon, this is a 3. So carbon number 2 have one methyl group, right? It is downside, so I am writing here CH3, CH3, and others 2 are hydrogen. Here what happened? Here we have upside one group is ethyl, right? Because 2 carbon is there, 1 2. Apart from this star carbon there are 2 carbon, that means ethyl group is present. So we will write ethyl on right side. We can write anyway. Here I am writing C2H5, C2H5. Now other 2 atoms are hydrogen again, right? Now draw in Newman. Backside carbon, this one, this is front carbon. As we want to draw eclipse, we will write this way. Here this carbon is C2. Now C2 has hydrogen on both the sides, and below side it has CH3, right? Now let's see the backside carbon. Backside carbon has C2H5 here, this place. Sorry for this one, C2H5. Please try to understand. I am not able to write properly. This C2H5, and this is H, and here also H. This is one of the eclipse conformation for this molecule. Now you can check here. This is similar to this one. If you will rotate it by 180, it depends on rotation only. The energy of these two conformations are same. These two conformers have same energy, because this C2H5 is interacting with hydrogen, then this CH3 is interacting with H. That means it has similar energy, but you can hold one carbon and other you can rotate by 60 to get the other conformation. Like suppose here I am holding the front carbon as it is here. Now I am rotating back side one by 60, from here to here. You can see 60 rotation of C3, rotation of C3, only one carbon. By rotating one carbon you can get different conformers related to the same configuration. So here if we will rotate by 60 back carbon, this C2H5 will comes to this side as we are getting here, right? But the energy of this conformation is high, very high, because this CH3 and C2H CH2 CH3 are interacting with each other, and it will give high energy. High energy means low stability, and the energy barrier is high here. Here if you will check from here to here, if you will rotate one carbon, backside carbon, by 120, not 60, sorry. If you will rotate 60, you will get staggered one. Sorry for the this confusion. Right here 120, 120. If you will rotate by 60, you will get staggered one. So if you will rotate by 120, you will get the another eclipse conformation. So here again 120 rotation of backside carbon, that means CS3, sorry, C3, you will get this one. This C2H5 will come this side here. This one is also one of the stable conformation. Again you have to rotate this one by 120 and you will get this one. You can see here, and the further rotation will give this again this one. So you can write all the conformations by rotating just one carbon here. Okay, so these are the eclipse conformation of the N pentane, but the most stable one is C and E. C and E. Here you can see the CS3 and CS2 CS3 interaction is less. The energy barrier is less compared to the other one. These eclipse conformations are more stable. Okay, then last one. Which molecule is this? Anyone? Anyone can guess? This is a cycloalkane, right? And we have 6 carbon atoms. That means it is a cyclohexane. Cyclohexane. Now all of you have read about this one. Cyclohexane have two types of conformations. There are different conformations, but the most stable one is chair conformation, right? More than two also is there. Half chair, half boat, boat, twist chair. Uh, there are different conformations, but this chair one is more stable. This one is the boat conformation of cyclohexane. Boat conformation. Sorry. Boat one. If you will rotate this way, you will get this one only. Boat one. So in boat conformation, we are taking 4 carbons for eclipse for drawing the Newman projection. So you have to imagine this carbon in one plane, and this carbon in one plane. Let's draw it. This carbon is backside one. I will draw little bit bigger. This is the backside carbon. This one, and this is front side carbon. Okay. Now again here also. Okay. Backside carbon, if you are considering this one, then one atom is going this way, another is okay. Sorry for the confusion. We are considering these 4 atoms, but from this side we will consider. I will write here from this side. That means this carbon will be our front carbon, and this carbon is the back one, and this carbon will be in same plane with this carbon. So this way we are taking this way. So first I will write this carbon here, then the backside carbon. I will give the numbering, that it will become better. 1, 2, 3, 4, 5 and 6. So 2 and 3 in same plane, and 5 and 6 is in same plane. So the front carbon is here, we are taking 2. 2, and the back one is third one. So you can see here the back carbon, look from this side, arrow side, is this way. This is the downside plane. I will write first here. First write this way, 3 substituents, and backside also has 3 substituents, right? Now draw the another one. You can see here these two are in plane, 5 and 6 are in plane, but 5 and 3 are joined by carbon number 4. This 4 is a substituent on third carbon, that means backside one. This backside one. This is backside one, right? So this is linked to the carbon number 5, which is the backside one of the 6 carbon. I will write this way, this carbon, right? And the carbon number 2 here and carbon number 6 have linked via carbon number 1, right? That means carbon number 2, this one, is linked to the front carbon, this one, via this carbon number 1. This is 1, this is 4, right? Okay. And all other atoms are hydrogen. This is not the atom, sorry. This is the eclipse conformation possible for cyclohexane. Boat conformation is nothing but the eclipse conformation of cyclohexane, and chair is always a staggered one, anti-conformation, staggered one. You can see in this image. As I told you, carbon number 1, 4 are is sharing between the two atoms. Carbon number 1 and 4. You can see 1 is shared between the 2 and 6, and the fourth one is shared between the third and fifth. This is the second carbon. This is the third one. I hope all of you are understand. And because these hydrogen atoms are interacting with each other, it's in eclipse conformation. The energy barrier is high here compared to the chair conformation. So this is less stable compared to the chair one. This is the eclipse conformation of cyclohexane, boat conformation. Boat conformation has only eclipse conformation, and chair is staggered one. Okay. I hope all of you are clear. If any doubt is there, you can ask me now, or we will stop here. And if you will get doubt later, then we can discuss in next lecture. Any question? Any doubt? Recording stopped already. You can see here also this is a boat conformation and these are eclipse conformations. Thank you for your attention. Let's discuss in the next class. Thank you so much.